When adding new electrical service to an existing building, understanding the grounding requirements is crucial. The purpose of a grounding system is to provide a low-resistance path to the earth. This is necessary for the proper operation of overcurrent protection devices, such as circuit breakers and fuses, and also to ensure the safety of people and equipment from electrical shock hazards. The minimum grounding electrode system for a building served by an electrical service consists of one of the following. Firstly, all grounding electrodes connected to the grounding bus in the service equipment. Secondly, a metal underground water pipe that is in direct contact with the earth for at least 10 feet. Thirdly, a metal frame of the building, provided that the frame is effectively grounded. This means the metal frame must be intentionally connected to a grounding electrode conductor. Fourthly, a concrete encased electrode, also known as a Ufer ground, that is not less than 20 feet long and at least 2 inches in diameter. Fifthly, an underground rod electrode, that is at least 8 feet in length. Sixthly, a plate electrode that has at least 2 square feet of area and is not less than 0.6 inches in thickness. Let's delve further into each of these grounding electrode options. Firstly, connecting all available grounding electrodes to the grounding bus within the service equipment is a fundamental practice. This ensures that all available paths to ground are utilized, which minimizes impedance and enhances the effectiveness of the grounding system. This approach leverages the combined grounding capabilities of multiple electrodes. Secondly, a metal underground water pipe can serve as an effective grounding electrode if it meets certain criteria. The water pipe must be in direct contact with the earth for a minimum of 10 feet. This requirement ensures sufficient contact with the earth to provide a low impedance path for fault currents. However, it is essential to verify the continuity of the water pipe and its connection to the main water supply, as non-metallic sections or insulating couplings can compromise its grounding effectiveness. Thirdly, the metal frame of a building can be used as a grounding electrode if it is effectively grounded. This typically involves connecting the building frame to a grounding electrode conductor, which in turn is connected to a grounding electrode. The metal frame must be continuous and provide a reliable path to ground. Proper bonding techniques are crucial to ensure that all sections of the metal frame are electrically connected and that there are no high impedance joints. Fourthly, a concrete encased electrode, often referred to as a Ufer ground, is a grounding electrode that is encased in concrete. This type of electrode must be at least 20 feet long and have a minimum diameter of 2 inches. The concrete must be in direct contact with the earth. Ufer grounds are commonly used in new construction, where the electrode can be easily installed during the foundation pouring process. These electrodes provide excellent grounding performance due to the large surface area in contact with the earth and the moisture-retentive properties of concrete. Fifthly, an underground rod electrode is a common and widely used grounding electrode. The rod electrode must be at least 8 feet in length and must be driven into the ground until at least 8 feet of contact with the soil is achieved. Rod electrodes are typically made of copper or galvanized steel. Multiple rod electrodes can be installed and bonded together to reduce the overall grounding impedance. Sixthly, a plate electrode is a grounding electrode that consists of a metal plate buried in the earth. The plate electrode must have a minimum surface area of 2 square feet and a minimum thickness of 0.6 inches. Plate electrodes are typically made of copper or galvanized steel. These electrodes are often used in locations where it is difficult to drive rod electrodes due to rocky soil conditions. Understanding the role of each of these grounding electrode options and their specific requirements is essential for ensuring a safe and effective grounding system. Consider the characteristics of the building and the local soil conditions when selecting the appropriate grounding electrode. Proper installation and bonding techniques are also critical for achieving optimal grounding performance. In situations where a building does not have access to a metal underground water pipe or a concrete encased electrode, alternative grounding methods must be employed. One common approach is to install one or more ground rods. The National Electrical Code, or NEC, specifies that a single ground rod is acceptable under certain conditions, but often 2 or more ground rods are required to achieve a sufficiently low grounding resistance. When using multiple ground rods, They should be spaced at least 6 feet apart to minimize the overlap of their effective grounding zones. The grounding electrode conductor, or GEC, is the conductor that connects the grounding electrode to the service equipment. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, in accordance with NEC Table 250.6C6. The grounding electrode conductor must be properly sized to safely carry fault currents back to the source. Proper bonding is another critical aspect of grounding. Bonding refers to the practice of connecting all metal parts of a building's electrical system together to create a low impedance path for fault currents. This includes bonding metal conduits, metal enclosures, metal water pipes, and other metal components. Bonding helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electric shock. The main bonding jumper is a conductor that connects the grounded conductor of the service to the equipment grounding conductor at the service equipment. The main bonding jumper provides a low impedance path for fault currents to return to the source, which helps to trip over current protection devices quickly. The size of the main bonding jumper is determined by the size of the service entrance conductors, in accordance with NEC Table 250.28. Equipment grounding conductors, or EGs, are used to ground non-current carrying metal parts of electrical equipment, such as metal enclosures, motor frames, and appliance housings. Equipment grounding conductors provide a low impedance path for fault currents to return to the source, which helps to trip over current protection devices quickly. The size of the equipment grounding conductor is determined by the rating of the overcurrent protection device protecting the circuit, in accordance with the NEC Table 250.122. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electric shock. GFCIs monitor the current flowing in the circuit and quickly interrupt the power if a ground fault is detected. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electric shock. Surge protective devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power line switching, and other events. Surge protective devices divert the surge current away from sensitive equipment, which helps to prevent damage. Regular inspections and testing of the grounding system are essential for ensuring its continued effectiveness. Grounding systems should be inspected periodically for signs of corrosion, damage, or loose connections. Ground resistance testing should be performed to verify that the grounding system is providing a low impedance path to ground. The results of the ground resistance testing should be compared to the recommended values in the NEC and other applicable standards. If the ground resistance is too high, corrective action should be taken to improve the grounding system. This may involve adding additional ground rods, improving the connections, or replacing corroded components. In summary, grounding is a critical aspect of electrical safety. A properly designed and installed grounding system helps to protect people and equipment from electric shock and fire hazards. By understanding the requirements of the NEC and following best practices for grounding, you can ensure that your electrical system is safe and reliable. When installing a new electrical service, there are several factors to consider regarding grounding. The first step is to determine the available grounding electrodes. If a metal underground water pipe is present and meets the NEC requirements, it can be used as a grounding electrode. If a concrete encased electrode is present, it can also be used. If neither of these options is available, ground rods or ground plates can be installed. The number and spacing of ground rods or ground plates will depend on the soil conditions and the required grounding resistance. The grounding electrode conductor must be sized according to NEC Table 250.66. The grounding electrode conductor must be connected to the grounding electrode and to the service equipment. The connection to the service equipment must be made at the neutral bus or at a point on the grounding bus that is bonded to the neutral bus. The equipment grounding conductors must be sized according to NEC Table 250.122. The equipment grounding conductors must be connected to the grounding bus at the service equipment and to all non-current carrying metal parts of the electrical system. All metal parts of the electrical system must be bonded together to create a low impedance path for fault currents. This includes bonding metal conduits, metal enclosures, metal water pipes, and other metal components. Ground fault circuit interrupters must be installed in all locations where they are required by the NEC. Surge protective devices should be installed to protect electrical equipment from voltage surges. Regular inspections and testing of the grounding system are essential for ensuring its continued effectiveness. Ground resistance testing should be performed to verify that the grounding system is providing a low impedance path to ground. The NEC provides specific requirements for grounding electrode systems. Section 250.50 covers grounding electrode systems and requires that all available grounding electrodes be bonded together to form a grounding electrode system. This ensures that all available paths to ground are utilized, which minimizes impedance and enhances the effectiveness of the grounding system. Section 250.52 covers grounding electrodes and specifies the requirements for various types of grounding electrodes, including metal underground water pipes, concrete encased electrodes, ground rods, and ground plates. Section 250.53 covers grounding electrode installation and specifies the requirements for installing grounding electrodes, including the depth and spacing of ground rods and the connection methods for grounding electrode conductors. Section 250.64 covers grounding electrode to conductor connections and specifies the requirements for connecting grounding electrode conductors to grounding electrodes into service equipment. Section 250.66 covers sizing grounding electrode conductors and specifies the requirements for sizing grounding electrode conductors based on the size of the service entrance conductors. Section 250.122 covers sizing equipment grounding conductors and specifies the requirements for sizing equipment grounding conductors based on the rating of the overcurrent protection device protecting the circuit. The NEC also provides requirements for bonding. Section 250.92 covers bonding of metal enclosures and specifies the requirements for bonding metal enclosures to ensure a low impedance path for fault currents. Section 250.96 covers bonding of metal water pipes and specifies the requirements for bonding metal water pipes to ensure a low impedance path for fault currents. Section 250.104 covers bonding of other metal parts and specifies the requirements for bonding other metal parts, such as metal conduits and metal building frames, to ensure a low impedance path for fault currents. In addition to the NEC, there may be local codes and regulations that govern grounding requirements. It is important to consult with the local electrical inspector to determine the specific requirements for your location. In summary, grounding is a critical aspect of electrical safety. A properly designed and installed grounding system helps to protect people and equipment from electric shock and fire hazards. By understanding the requirements of the NEC and following best practices for grounding, you can ensure that your electrical system is safe and reliable. When adding new electrical service to an existing building that has never had electrical service, the inspector can't require a Ufer ground if one doesn't exist. The Ufer ground is a concrete encased electrode and is an option if the building has a poured concrete foundation. If the building doesn't have a concrete foundation, then it is not required. Bonding to the steel framing and installing a supplementary ground rod might not be adequate, depending on the local electrical codes and the inspector's interpretation. It is important to consult with the local electrical inspector to determine the specific grounding requirements for your location. It may be possible to install an additional rod and bond the two rods together through at least a number 2 copper or aluminum conductor. This can extend the effective length of the supplementary electrode and satisfy the code requirements for an 8-foot electrode. The grounding electrode system provides a low resistance path to the earth, which is required for the operation of overcurrent devices and for the protection of life and personnel against electric shock. There are different types of acceptable grounding electrodes. These include metal underground water pipe in direct contact with the earth for at least 10 feet, the metal frame of the building if it's effectively grounded, a concrete encased electrode not less than 20 feet long and at least 2 inches in diameter, an underground rod electrode 8 feet in length and a plate electrode at least 2 square feet in area and not less than 0.6 inches in thickness. Given the limited options, installing an additional 8-foot ground rod next to the existing supplementary grounding electrode and connecting the two rods together with an insulated number 2 copper or aluminum conductor may be a way to meet the grounding requirements.